All right, guys, let's start. So now we are doing your lesson number 3 of your chapter number 1. Okay, and it is about interpolation, basically interpolation and your extrapolation, right? Very interesting chapter. We are still continuing with our chapter number 1, which is Introduction to Numerical Method in Finance, right? So very, very important. Okay, so let's go slide by slide. Try to keep it simple but strong and connecting each concept to your pricing, your risk management, your portfolio management, and quant finance use cases, right? The lecture is about your interpolation, extrapolation techniques in your numerical finance. First of all, the big picture in finance, we rarely have market data at every possible point. For example, let's say we have financial objects, right? Yield curve. Data we observe is 1 year, 2 year, 5 year, 10 year yield rates, then volatility surface, volatility at selected strikes or maturities, right? Bond pricing, which is price at known maturity, then risk model, which are historical prices with gaps, stress testing, which has historical observed scenarios. And for yield curve, let's say we need data we often need is like 3 year, 7 year, 8.5 year rates, right? We already have 1 year, 2 year, 5 year, 10 year rates, which we observe, but we also need some other data, right? For which we need interpolation, extrapolation. Volatility surface, we have volatility at selected strikes or maturity, right? But we might need volatility for any strike or maturity. Similarly, bond pricing, we have prices at known maturity, but we might need price or yield at an unquoted maturity. For risk models, we have historical prices with gaps, but we need complete time series, right? For stress testing, we have historical observed scenarios, but we often need extreme future scenario, right? So we use techniques such as interpolation, meaning estimate inside data range, reliability is more reliable. Extrapolation, estimate outside known data range, less reliable, more risky, right? And since this lecture belongs to numerical analysis in finance, the central idea is how do we estimate missing values when market gives us only discrete data points? In quant finance, this comes up everywhere. So you look at yield curve, your option volatility surface, your forward curves, your credit curves, your risk factor grids, and missing time series data. Okay. Fine. So now we have introduction to interpolation and your extrapolation. You look at the core concepts, right? So if you look at your data for interpolation and extrapolation, please understand interpolation and extrapolation, right? Your interpolation and extrapolation are numerical techniques used to estimate your unknown value based on a set of known data points. These methods are essential in finance when market data is often available only at discrete points. We look at definitions, interpolation, estimating values within the range we observe data point, extrapolation, estimate values outside the range of observed data, which we know, right? Why they matter in finance? Financial data is typically discrete, not continuous. Many pricing risk model requires value at unobserved points. Accurate estimation, improve value and risk assessment. Key application in finance, interest rate curves, optional pricing, time series analysis. Key insight is interpolation is generally more reliable than extrapolation. Careful method selection is critical for financial accuracy, right? Simple point is interpolation means estimating a value within the range of known observation. For example, maturity can be 2 year, yield 4%, maturity can be 4 year, yield 6%. You want the 3 year yield since 3 year lies between 2 year and 4 year. This is interpolation. Extrapolation means estimating a value outside the range of known observation. Yields up to 10 year, but you want a 30 year yield. That's extrapolation. Why this matter in finance? Because financial data is usually discrete, but models often require continuous input. Especially in the area of bond pricing, by estimation needed because you need discount rates for every cash flow date. Option pricing need implied volatility for any strike and maturity. Risk management need risk factor values at unobserved points. Portfolio optimization need expected returns, volatility correlation, sometimes filled with incomplete data set. Main message is interpolation is safer because it stays inside observed data. Extrapolation is dangerous because it projects beyond evidence. And then we get into your linear interpolation, right? Let's try to understand this concept. Again, we have to understand the formula, the interpretation, and the example. This is the simplest and most important starting point. The idea is between two known points. Assume the relationship is straight line. Suppose we have two known points, x0, y0, x1, y1. The linear interpolation formula is given here. Y of x equals y0 plus y1 minus y0 divided by x1 minus x0 multiplied by x minus x0. What each part means is x0, x1 are the known x values, such as maturity. Y0, y1 is known y value, such as yield. Y1 minus y0 divided by x1 minus x0 is slope between the 2 points. x minus x naught, how far the required point is from the first known point, y x is estimated value as x. Financial example, again, as I said, right, we can use value 2 year, let's say 4%, 4 year, let's say 6%. You put the value, right, estimate the 3 year deal. If I have to find y and I have to find y3, right, y3 is what? Y3, if I have to find 3 year yield, y3 is equal to what? 4% plus 6% minus 4% divided by 4 minus 2, and here it is 3 minus 2. Right, you solve it, you get 5%. Right. So quant finance connection is linear interpolation is used when we need quick estimates, especially in yield curve, estimate 3 year rate from 2 year and 4 year rate, volatility curve, estimate applied volatility between two strikes, bond valuation, discount cash flow falling between quoted maturity risk, estimate missing market risk factor value, but the weakness is clear. Financial curves are often not perfectly straight, and that is what we need to understand. And then we get into the next part, which is your Lagrange interpolation, right? Now we move from your straight line to curves, right? And we have to understand the Lagrange, also some people call it polynomial for n data points. We have to understand key property and example. So now we move from straight line to curves. Polynomial interpolation fits one polynomial that passes exactly through all known data points. The general Lagrange formula is given as this. What does this mean? This is P of x equals the sum from I equals 0 to n of y, I times L I of x. Here Li x is the Lagrange basis polynomial, right, which is given, and the equation is this. Li of x equals the product over all j not equal to I of x minus xj divided by xi minus xj. What's happening intuitively? Each Lix acts like a weight attached to one data point. The polynomial combines all points in such a way that Pxi is equal to yi. This means the curve passes exactly through every observed point. Simple interpretation is linear interpolation, 2 points connected by a straight line. Polynomial interpretation, all points connected by one smooth global curve. Finance uses polynomial interpretation, can be used for areas such as asset area, uses estimate intermediate price level, economic data, estimate missing data between reports, and term structure, approximate rates between maturity. But there's a warning, right? High degree polynomials can oscillate badly. This is called your rung phenomena, right? Rung phenomena we have, right? And in finance, that can create unrealistic curves, for example, strange implied volatility spikes or yield curve humps that are not economically meaningful, right? So that is what happens here. Okay, so that's the main part here. Then we go to the next part, which is your cubic spleens and your smooth interpolation, right? Cubic spleens and your smooth interpolation. Okay. So then we talk about cubic spleens and smooth interpolation, cubic spleen characteristics, why spleens are preferred and application in finance. Right? This is one of the most practical slides in the lectures. Spleen interpolation solve the problem of using one big polynomial. Instead of fitting one global polynomial, spleens fit piecewise polynomials. That means use smaller curve between each pair of data points to connect them smoothly. A cubic spleen uses cubic polynomial between points. A cubic polynomial has the form of your SIX is equal to AI BIX plus CI x squared DI x cube. SI of x equals AI plus BI x plus CI x squared plus DI x cube. What cubic spleen ensures is that if your property is, let's say, function continuity, meaning the curve does not jump. If your property is first derivative continuity, meaning the slope is smooth. If the property is second derivative continuity, meaning the curvature is smooth in finance, the smoothness matters a lot. For example, in your yield curves, we do not want artificial jumps in interest rate. In volatility services, we do not want strange discontinuous across strikes or maturity. But spleens are preferred because problem with high degree polynomial is if it is oscillation, how spleens help is that piecewise fitting reduces your instability. If too sensitive data, local fitting is more stable. If bad boundary behavior, okay, smoother and more controllable. Unrealistic financial curve, better shape for yield curve and volatility curves. Financial implications. If your finance area yield curve construction, spleen use is to build your smooth discount of zero on the forward curves. Option pricing, spleen uses to estimate your option prices across cycle maturity. If volatility services, it is for smooth implied volatility grade. If it is risk management, sensitivity calculation needs smooth input. This is very important practice because many curve building frameworks use spleen-like methods because the output must be smooth, stable, and usable for pricing and Greeks. Okay. Then we look at your spleen interpolation, right? Spleen interpolation, the slide repeats the same spleen content. So instead of repeating mechanically, let's reinforce the core exam or the interview point. The key learning from slide 5 and 6 is spleens are preferred because they balance two things. First is your requirement. If your requirement is fit market data, white matters in finance because curve shape observed or curve shape match your observed codes. Requirement is stay smooth. White matters in finance because curve shape not create artificial arbitrage or unstable briefs. For example, suppose you are building a volatility surface. You observe implied volatilities for a few strikes, right? So let's say you have a strike 90. And implied volatility 24%. If you strike 100, 20%. If you strike 110, 22%. Now, you may need volatility strike 105. A spleen gives a smooth estimate, while a high degree polynomial may overreact and produce weird shapes. Risk management, unstable interpolation can produce unstable Greeks, war, stress losses, or hedge ratios are very important here. Okay. So, cubic spleen characteristic uses cubic polynomials between each pair of points. Ensure continuity of the function, ensure continuity of first and second derivatives. But spleens are preferred because avoid oscillations seen in high degree polynomials, produce smooth curves suitable for financial data, stable for large data sets. Application in finance, yield curve construction from discrete maturities, often pricing estimate price across strikes and maturity, volatility surface, and term structure modeling. Okay. Then we get into the next part, which is your extrapolation techniques, estimating beyond your observed data. So we look at your key characteristics, common extrapolation approaches, and application in finance. We move outside the known data range. Extrapolation means estimating values beyond the observed minimum or maximum data point. For example, known data yield curve up to 10-year, required value need 30-year yield. Known data volatility surface up to 2-year maturity, required value need 5-year. Option volatility, known data is historical data till today. Required value need future projected return. This is inherently riskier because we are assuming the past and continuous. Type of extrapolation, method is linear extrapolation, idea is extend boundary slope, method is polynomial extrapolation, idea is extend Phillips polynomial, method is model-based extrapolation, idea is use economical financial theory. Financial application is use case, long-term interest rate example, 30-year rate from term maturity, cash flow projection, forecast your future, revenue or asset value, stress testing example is estimate losses under extreme scenario, risk management, project risk factors beyond your observed market conditions. Main message is extrapolation is not just numerical, it is assumption heavy. That is why it is dangerous in your financial risk. Then we get into your concept and formula for your linear extrapolation. Linear extrapolation has the same formula as linear interpolation, right? Same formula, but now x lies outside the interval. For example, x is greater than x1, right? Or x is less than x0. Suppose maturity 5-year, 5%, 10-year, 6%, the slope is 6% minus 5-year, 10 minus 5, 0.2% per year. We extrapolate to 15-year, right? So y15 is what? Y15 will be 5% plus 0.2%, 15 minus 5, which comes out 7%. Okay. But is that reliable? Maybe not. It assumes the yield curve continues with the same slope from 10-year to 15-year. In real market, long-term rates may flatten, invert, or be driven by central bank policy. So inflation expectation, liquidity premium, and term premium also affects it. Okay. Key point is linear extrapolation is acceptable only for short-range extrapolation. In risk term, short extrapolation sometimes acceptable. Short extrapolation, lower model risk. Short extrapolation, easier to justify. Long extrapolation, very risky. High model risk needs stronger economic assumption. Then we get into polynomial extrapolation, extending polynomial fits. Polynomial extrapolation fits a polynomial to observe data and then evaluate it outside the observed range. Main idea is your px used for x outside known range, but this is dangerous. For polynomial may fit historical data beautifully, but outside the range, it can explode. For example, a high degree polynomial fitted to yield may produce problems such as large oscillation, which is unrealistic yield curve, sensitivity to noise, bad valuation, explosive projection, wrong risk estimate, boundaries instability, incorrect hedges. The quant finance warning here is polynomial extrapolation is especially risky for forecasting asset prices, returns, volatility, or interest rate. Why? Because markets can have your different things. If the market issue is regime change, effective old trend stops working. If the market issue is structural break, Effect is model becomes invalid if market issue is volatility shock. Effect is smooth fitted curve fails. The market issue is policy shock. Effect is interest rate projection breaks. So in real finance, polynomial extrapolation is usually avoided for long-term projection. Okay. Then, so we look at the general idea, limitations, and practical insight. Okay. Then we get into the next part, which is your exponential and logarithmic description, logarithmic extrapolation, growth, and decay models. So the slide introduced exponential growth decay model. The formula is V of t equals V naught times exponential to the power RT, meaning Vt is the value at future time t, V naught is initial value exponential, constant approximately 2.718, R is the growth or decay rate, T is time. This formula is used when growth compounds continuously. Financial connection is this is very important because finance often uses compounding. For example, if an investment grows continuously at rate R, your Vt is equal to V naught exponential RT, V naught is equal to 100, R is equal to 5, T is equal to 2, right? If we take those values, let's say V2 is equal to 100 exponential 0.05 into 2. When we have taken V naught is equal to 100, R is equal to 5, T is equal to 2. So value comes out as approximately 110.52. Where this appears in quant finance, because let's say we are doing continuous compounding, right? Formula connection is FV is equal to PV exponential RT. If we are doing discounting, PV is equal to FV exponential minus RT. Blackstone uses exponential discount factor. Asset price modeling uses growth often model exponentially. Risk neutral pricing uses discount expected payoff using your exponential discounting. Important distinction is that linear model adds same amount each period, suitable for simple trends, can become unrealistic for finance. Exponential model grows by same percentage, suitable for compounding, often more natural for asset growth. But even exponential extrapolation can be dangerous if R is assumed constant for too long. And that is what are the typical applications we have, right? Bond interest and investment growth, asset price modeling, and the constant growth assumption, long-term interest rate prediction. Then we get into your slide number 11, which is extrapolation in finance, which is practical consideration. While extrapolation can be useful, it introduces significant uncertainty because it relies on assumption about your future behavior. Key risk of extrapolation, structural breaks in financial market, regime changes in interest rate volatility, model risk dominate data-driven inference. Best practice, prefer interpolation whenever possible, use model-based extrapolation with economic justification, perform sensitivity and stress testing. Key insight is extrapolation should support scenario, not prediction. Results must be interpreted with caution in risk management, right? So again, this is a risk management slide. The slide says extrapolation introduces significant uncertainty because it depends on assumption about future behavior, key risk, structural breaks, meaning market relationship changes suddenly, regime changes, interest rate volatility, environment shift, model risk, wrong model dominates the answer. Simple idea, example, interest rate. Suppose you extrapolate long-term rate based on short-term rate. But then, see, event is central bank changes policy, impact is curve shift. Event is inflation expectation changes, impact is long-term rates move. Event is crisis happening, safe haven demand, your changes yields. Event is liquidity rise up, market code becomes unreliable, your extrapolation may fail badly. Best practices, if we prefer interpolation, right? Uses observe market range. If you prefer or your best practice for economic logic, extrapolation should not be pure math. Best practice for sensitivity testing, check how inputs output changes. Stress testing, test extreme but plausible cases. The key line is extrapolation should support scenarios, not prediction. It's excellent risk management thinking. In other words, we do not say that 30-year rate will be 7%. Instead, we say under this extrapolation scenario, 30-year rate is estimated at 7%, but we must test alternatives. Okay. Then we get into your applications of interpolation and extrapolation in finance, the financial use cases, the key application, optimal pricing, yield curve construction, missing data and financial time series, risk modeling, and key insights, right? So slide brings the whole lecture into finance, option pricing in Black-Scholes. Option value depends on volatility, but the point here is that market implied volatility is available only at selected strike and maturity. So build an implied volatility surface. Input needed, your volatility for exact strike maturity. Problem is market codes are discrete. Solution is interpolate volatility surface. For example, let's say you need implied volatility for K is equal to 103, T is equal to 9 months. But market codes are available for 6 months and 1 year only. So you interpolate across both strike and maturity. Similarly, yield curve construction, bond cash flow may occur at dates where there is no direct observable market rate. So we interpolate it. Example, a bond pays a coupon in 3.5 years. But market quotes exist for 3 year and 4 year, right? So you estimate that we find 5 year discount rate. That affects your bond price, which impacts your discounted cash flows, duration, which impacts your interest rate sensitivity, value at risk, which impacts your risk factor shock, hedging, to which maturity bucket to hedge. You have missing financial time series, sometimes data has gap, missing prices, missing FX rates, missing macro data. Interpolation can still missing values, but be careful for your traded prices. Blindly filling missing data can distort volatility and correlation. Risk modeling and forecasting also. Extrapolation is used in scenario analysis and stress testing. So if your scenario is equity crash, extrapolation uses estimate portfolio value beyond historical move. If your scenario is rate shock, project yields beyond your observed curve. If your scenario is credit stress, estimate default spread widening. If your scenario is volatility spike, estimate option losses under extreme volatility. So that is what we do. And then once we have done that, we move to the next part, which is your, again, the same thing, right? It's a repetition of the slide, so don't bother too much. But the idea is very simple, that we are kind of strengthening the application, the same concept across finance. If your topic is yield curve, interpolation role is estimate rates between maturity. Extrapolation role is to estimate rates beyond lost maturity. Volatility surface, interpolation role estimate volatility between strikes or maturity grid points. Extrapolation role estimate long dated or far OTM volatility. Portfolio risk, interpretation role fill missing market data. Extrapolation role stress unseen scenarios. If the topic is portfolio optimization, interpretation roles complete return variance inputs. Extrapolation role forecast return, expected return. Credit risk, interpolation role is interpolate survival default probabilities. Extrapolate project long-term default risk. The important portfolio optimization link here is that portfolio optimization often needs mu, sigma, rho kind of summation, and we have volatility, expected return, correlation, sigma, coverage metrics. If data is missing, interpolation may help complete the data set, but extrapolating expected return is dangerous because returns are noisy and unstable. So in portfolio management, interpolation can support data cleaning. Extrapolation should be treated as scenario assumption, not truth. Okay, then we get into next slide, which is key takeaways, core concepts and application in finance and implementation insight. Basically, the slide summarizes the lecture. The concept is interpolation, meaning estimate inside known data range. Extrapolation, estimate outside known data range. Linear interpolation, straight line estimate. Polynomial interpolation, one curve through all points. Linear interpolation, smooth piecewise curve. Linear extrapolation, extend straight trend. Polynomial extrapolation, extend binomial kind of fit. Exponential extrapolation, use compound growth decay model. The financial application is, if your application is bond pricing, technique is yield curve interpolation. Application is option pricing, technique is volatility surface interpolation. Application is time series, technique is missing data filling. Application is risk modeling, technique is scenario and stress extrapolation. Application is forecasting, model-based extrapolation. The implementation inside is the slide mentioned Python libraries such as SciPy, common tools, NumPy, interrupt, which is simple linear interpolation, SciPy, interpolate, screens and advanced interpolation, visualization, check curve shapes and extrapolation risk. In real quant work, visualization of the curve is not optional. The curve may fit numerically but still look economically wrong, which is very, very important. Okay. Then we get into the next part. So again, theoretical question, interpolation versus extrapolation. Define both mathematically. So mathematically, interpolation is what? Fx, where x falls between your x1, comma xn. F of x, where x belongs to the interval x1 to xn. Extrapolation is what? Fx. The x does not fall into your x1, xn. Okay. Why interpolation is more reliable? Because uses observed range, lower uncertainty, less model dependence, better for pricing. Extrapolation goes beyond your observed range, higher uncertainty, more model dependence, better for scenario analysis. Right? Financial risk example is estimate a 5-year yield from 2-year and 10-year market yield is interpolation. Estimating a 50-year yield when the market has reliable quotes only up to 10-year is extrapolation. The 50-year yield estimate carries much higher model risk. Okay. Question number 2, linear interpolation, estimated 3-year yield from 2-year, 4% and 4-year, 6%. This we have done in one of the example also. Y is equal to y1 plus x minus x1, x2 minus x1, your y2 minus y1, So you substitute y is equal to 4% plus 3 minus 2, 4 minus 2, 3 minus 2, 4 minus 2, 6% minus 4%, which comes as your 5%. Okay. So assumption is, if your assumption is your linear relation, meaning yield moves in straight line between 2 year and 2 year and 4 year. If your assumption is smooth yield curve, no sudden jumps between maturity. If your assumption is no curvature, ignores convexity, humps in the curve. The practical validity is linear interpolation is simple and fast, but it may ignore curvature. In real market, yield curves often bend, so forth. Professional curve construction, screens, and more advanced curve methods are often preferred. Okay. So that is what we have. And again, you understand the practical validity, right? Linear interpolation is simple and fast, but it may ignore curvature. Then we get into your polynomial spline, polynomial versus spline. See, if you compare the method, if your feature is curve type, polynomial interpolation is one global polynomial, spline interpolation is piecewise polynomial. Fit is polynomial interpolation is passes through all points. Spline interpolation passes smoothly through near points. Stability, polynomial interpolation can be unstable for large n. Spline interpolation more stable. Oscillation risk, polynomial interpolation high. Spline interpolation lower. Finance risk, polynomial interpolation limited use. Spline interpolation more common for curves. Then we have Runge phenomena. Runge phenomena means high degree polynomial interpolation can oscillate strongly, especially near boundaries. Simple where the curve tries too hard to pass through all points and start behaving wildly in finance. This is dangerous because it can create fake market signal. Example, if your curve is yield curve, bad oscillation effect, unrealistic forward rates. If your curve is volatility curve, arbitrage like volatility shapes. If your credit curve, strange default, probability patterns. Conclusion is spleens are usually preferred for yield curves and your volatility surface, right? So remember that point. Okay. Then we get into your next part. Question number 4 and 5. Question number 4 is about extrapolation in finance, linear versus exponential extrapolation. Linear extrapolation assumes a constant absolute slope. Exponential extrapolation assumes constant percentage growth or decay. Linear interpolation, the formula is y is equal to a plus bx. Exponential is vt is equal to v naught. Exponential rt. Linear is best suited for short extension. Exponential is for compounding growth decay. Example of exponential use stock growth price or investment value under constant growth. ST is equal to S naught E GT, where ST is stock, future stock value, S naught is the current stock value, G is the growth rate, T is the time. Risk is model breakdown, explanation, growth rate may not remain constant, overestimation, exponential models can explode. Risk is still risk pricing, explanation is extreme outcomes may be underestimating, risk is regime shift, historical trend may stop kind of working. Okay, so that is what we are looking for. And you can Python implementation for interpolation. We have, we can see the code in the end, guys. I think that will give you much more better idea, right? We can go to the solution because code I can't write everything here. All solutions are here, guys. I'm going to the code part. So idea here is that interpolation we use numpy.interp, right? So that is what we do. SciPy.interpolate, extrapolation used partially with trend models, limit your horizon, visualization, detect overfitting, validate smoothness, compare actual versus your fitted curve. So if you limit your extrapolation horizon, because long range extrapolation is unreliable, if you use your economic logic, because pure trend extension is dangerous, run sensitivities because check how output changes, visualize because spot unrealistic behavior, right? So that is what we need to know. Okay. So that is what we need to know, right? And yeah, so that is what we have. And then we have the solution, right? Which I told you, right? For each question, we have the solution. I have given you all the answers. You can go and check the answers in detail also, right? So that's not an issue. But remember that, right? So overall, please understand in quant finance, we do not calculate the curve. We also inspect whether it makes financial sense or not, right? So if you're looking at linear interpolation, the formula idea is straight line between 2 points, strength is simple and transparent. If you're looking at polynomial interpolation, formula idea is one polynomial through all points. Strength is exact fit. If your method is cubic spline, Formula idea piecewise cubic curves. Strength is smooth and stable. Weakness is more complex. Used for yield curves, volatility surface. Similarly, polynomial interpolation. The weakness is oscillation risk. Finance use case is small data sets only. If your method is linear interpolation, weakness is nose curvature. Finance use case is quick yield volatility estimate. If your method is linear extrapolation, formula ideas extend boundary slopes. Strength is simple. Weakness is unsafe for outside range. Managed use cases, short-term projection. If your weakness is polynomial extrapolation, formula ideas extend fitted polynomial. Strength is flexible. Weakness is very unstable, usually avoided in finance. And if your exponential extrapolation, VT is equal to V naught exponential RT, strength is natural for compounding. Weakness is constant growth assumption. Investment growth and discounting are the financial use, right? The core lesson is interpolation, extrapolation are not just mathematical tricks, they directly affect your pricing. Input like rates and volatility determine your fair value. Risk management, bad curve creates wrong war, stress losses, risks. Weeks, portfolio management, missing data and forecast affect your optimization. Hedging, smooth curve produces more stable sensitivities. Forecasting, extrapolation must be treated as scenario based. The clean takeaway here is that interpolation fills a gap inside your known market data. Extrapolation projects your beyond known data and carries much higher model risk. For real quant finance, use interpolation for pricing, use extrapolation carefully for scenario and stress testing. Okay. So that's it, guys. That's it for this chapter. Not a very long chapter. Go back and revise it. Once you've done it twice, I think you'll be totally fine. That's it from my side, guys. Go back, revise it, and see you in the next chapter. Okay. Thank you. Not a very difficult topic, guys. Easy topic. Just quickly revise it and you'll be fine. All right, guys. Thank you.